In this example, we're going to be asked to calculate a 99% confidence interval. A 99% confidence interval for a sample mean. And that sample mean is the confidence interval. That sample mean is of size 50, and it turns out it's 15.21. We know it comes from a normal population, which has an unknown mean, but a standard deviation which is known and is 0.5. There's bits of information we can already get down on paper. So we can say that n is equal to 50. We can say that x bar, the symbol for sample mean, is 15.21. It's a sample taken from a normal population, but remember we know a lot about what this will be distributed as itself. This is a data item from a new distribution, and that new distribution will be the distribution of all such sample means, and they'll be distributed normally, as the parent is, with the same mean as the parent. Even though that's unknown, it will be the same as the unknown mean, but with a variance the same as the parent population divided by the sample size. And of course we know all of that by the central limit theorem. Now what does the confidence interval provide us with? Let's take the first example. Let's say that we have all our data items calculated somewhere between minus infinity and plus infinity. So let's say the first example we have there is 50, gave us a mean of 15.21. So it just happens that they look like that. When we've calculated it, that was the full extent, the line that had all the 50 samples on it, and we're going to calculate a confidence interval that places it between here and here. Now you might be thinking, well, how? I'll explain that by using the distribution. We know from this that that's what the distribution will look like. It will be normal, and using that mean, it will have the same mean as the parent distribution. We also know, of course, that we can standardize from our z-variate. Of course, we know we can calculate values such that these n's here and here are going to be 0.5%. The reason I choose them to be 0.5%, of course, is because I want the middle bit to be 99%. So I can look up these values, if you like, ZB and ZA, on my calculator. I'll show you how to do that in a minute. Because if we have those values, we can standardize them to our current distribution. We essentially use the mean we've got, and we say, well, it's going to be up here, we'll need to find the corresponding values, and down here the corresponding values, and this value A and B are these values A and B on my confidence interval. Now to get that value, we know we're going to have to multiply the Z value by the standard error. But of course we have the standard error. It's sigma squared over n square rooted. So to calculate this, it's going to be x bar add the ZB value times by the square root of all of this. Of course, at this end, it will be x bar subtract the ZB value times by this. And of course, those two values there will provide us with our confidence interval. Now, what could happen now? What can we say about that confidence interval? Well, of course, if we then go and take another 50 samples, there's no way it's going to be the same. The next one may turn out to look like that. The next one like this. The next one like this. The next one like this. The next one like that. All we can say, and this is what a confidence interval is that if we did, shall we say, 100 of these, we'd have a 99% probability of 99 of those intervals covering the actual true mean. Let's do a sort of example on, let's say the true mean is Let's say it's here. Well, it's in this one, it's in this one, it's in this one, it's in this one. It's just missed out on that one and that one. So what I'm predicting, the confidence interval helps us predict, is that if we did 100 of these, we'd expect to find 99 of them. And as you can see, my example would appear to be already slightly out. But that's the prediction.